Imagine an object in space that you could never enter. No spacecraft could cross its boundary. No particle could fall inside. Not even light could move inward through its horizon. But matter and energy could come rushing out. This theoretical object is called a white hole. White holes are often described as the opposite of black holes. A black hole allows matter and light to cross its event horizon inward, but nothing that passes that boundary can return to the outside universe. A white hole would reverse this rule. Matter and light could escape from it, but nothing outside could enter. This sounds like science fiction, but the idea comes from real mathematics inside Einstein's theory of general relativity. To understand white holes, we first need to understand what an event horizon really is. An event horizon is not a solid surface. It is a boundary in space-time. Around a black hole, the geometry beyond that boundary is arranged so that every possible future path leads farther inward. A rocket could fire its engines at full power, but once it crossed the horizon, escaping would require moving faster than light. That is impossible. A white hole horizon would have the opposite structure. Every future-directed path inside it would lead outward. An object approaching from outside would find no allowed future path that carried it through the horizon. It would not be blocked by a wall or pushed away by a mysterious force. The structure of space-time itself would prevent entry. One simple way to imagine a white hole is to reverse a film of a black hole. Play a video of gas falling into a black hole backward, and the gas appears to emerge from the horizon and spread into space. Mathematically, some solutions of Einstein's equations allow this time-reversed region. The most famous example comes from the complete mathematical extension of an eternal Schwarzschild black hole. This idealized solution contains a black hole region, a white hole region, and additional regions of space-time. But this does not mean that every real black hole contains a white hole. Astrophysical black holes form when massive stars collapse or when compact objects merge. The space-time produced by a real collapse does not automatically include the eternal white hole region found in the ideal mathematical solution. That creates the first major problem. We know several natural processes that can form black holes, but we do not know any confirmed natural process that creates a classical white hole. A white hole appears to require extremely special initial conditions. Matter must somehow begin inside the white hole region and emerge in a carefully arranged way. The universe would need to begin with this configuration already prepared. That makes classical white holes seem physically unlikely. There is an even bigger problem: stability. Space is not perfectly empty. Radiation, gas, dust, and particles are constantly moving through it. Research on white hole geometries suggests that even small disturbances near the horizon could strongly affect them. In many classical models, incoming matter can destabilize a white hole, or cause the white hole geometry to collapse into a black hole-like state. A large white hole might therefore be extremely difficult to preserve in a realistic universe. This is one reason many physicists treat white holes as mathematical possibilities rather than known astronomical objects. White holes are also frequently connected to wormholes. The complete, eternal black hole solution includes a structure called an Einstein-Rosen bridge. It links different regions of the mathematical space-time diagram. One side is associated with a black hole region, while another is associated with a white hole region. But this bridge is not a safe tunnel through space. It closes too quickly to be crossed. A traveler entering the black hole could not simply fly through the bridge and emerge from the white hole. The traversable wormholes of science fiction require very different conditions, often involving exotic forms of matter that have never been shown to exist in the necessary form. So a white hole is not automatically a portal to another galaxy or another universe. Then why are physicists still interested in them? Because black holes create a deep conflict between general relativity and quantum physics. According to classical general relativity, matter collapsing inside a black hole continues toward a singularity. At a singularity, the theory predicts that space-time curvature becomes unbounded, and the ordinary description of physics breaks down. Many physicists believe this means general relativity is incomplete under such extreme conditions. A future theory of quantum gravity may replace the singularity with a new physical process. Some quantum gravity models propose that collapse does not continue forever. Instead, matter may reach an extremely dense quantum state and then bounce. The collapsing black hole interior could transition into an expanding, white hole-like region. Matter and information that entered the black hole might eventually emerge again. This is called a black-to-white hole transition. Several models inspired by loop quantum gravity have explored this possibility. Some describe the transition as a form of quantum tunneling between black hole and white hole geometries. Others investigate whether a very small white hole remnant could survive after a black hole loses most of its mass through Hawking radiation. These ideas are fascinating, but they are not established facts. Physicists do not yet have a complete, experimentally confirmed theory of quantum gravity. Different models predict very different transition times. In some versions, the change might happen rapidly inside the black hole, but appear incredibly slow to a distant observer because of gravitational time effects. Other versions predict that a black hole could remain black for an enormous period before entering a white hole phase. Some proposals suggest that tiny white hole remnants might store information for extremely long periods. They have even been discussed as possible components of dark matter. But none of these possibilities has been confirmed by observation. So what would a white hole look like through a telescope? In theory, it might release matter and energy in a powerful outward event that could resemble a cosmic explosion. But the universe already contains many violent events. Supernovae explode when stars die. Gamma-ray bursts produce enormous flashes of high-energy radiation. Neutron star mergers throw matter into space. Active galaxies can produce powerful jets. An unexplained explosion is not automatically evidence of a white hole. To identify one, scientists would need a distinctive prediction that separated it from ordinary astrophysical events. They would need evidence of a one-way horizon that allowed matter to emerge but could not be entered from outside. No observation has yet demonstrated such an object. NASA's astrophysics material describes white holes as theoretically possible but unsupported by observational evidence. 3. The Big Bang is also sometimes called a white hole. At first, the comparison seems tempting. Matter and energy emerged during the early universe, and we cannot travel backward beyond its earliest known stages. But the comparison is misleading. A white hole would be a localized region inside a larger space-time. The Big Bang was not an explosion from one point into empty space. It describes the early hot, dense state and expansion of space throughout the observable universe. Calling the Big Bang a giant white hole may be a useful analogy in casual conversation, but it is not the standard cosmological description. White holes teach us an important lesson about theoretical physics. A mathematical solution can be allowed by an equation without being created by nature. Einstein's equations permit many possible space-time geometries. Some describe objects we observe, such as black holes. Others may require unrealistic initial conditions, or may be too unstable to survive. White holes could belong to that second group. But quantum gravity leaves the door slightly open. Perhaps white holes do not form as giant objects in ordinary space. Perhaps they appear only briefly during the final evolution of black holes. Perhaps tiny remnants exist but are extremely difficult to detect. Or perhaps white holes are mathematical shadows with no physical counterpart at all. At present, black holes are supported by extensive astronomical evidence. White holes are not. They remain hypothetical objects at the border between established relativity and unfinished quantum gravity research. And until we discover a clear observational signature, the strangest thing about a white hole may be this: the equations allow it, but the universe may never build one. Subscribe for more strange mysteries of space and physics.